Let's talk about the second law for a second and then move on to efficiency. Okay, guys. So given an engine, right, we provide that with some fuel and it can do some work. That's the whole funda of engine, is it not? But the second law also tells that as a part of this entire system, as in when you give heat in, right, some work is done, yes, and also some of the energy has to go to your cold reservoir. So this is your cold sink, yeah. So that's your heat sink. So this has to happen, right? This needs to happen. So clearly QH is not going to be equal to W. So this is a limitation that the second law puts. So the next obvious question is, what is the efficiency of a given engine? Right? What is the efficiency of a given engine? If this is the case, then we have to talk about efficiency. So what is efficiency? Efficiency is nothing but a simple basic idea of efficiency is nothing but how much effort are we putting in and how much output we are getting out of it. So what is the result that we are getting out for the effort that we are putting in, right? So you can call it as result, you can call it as whatever you want. For a given effort, for the given work, what is the result we are getting? That's your efficiency, right? A very good efficient vehicle, not vehicle per se, engine will give us a lot better output. For example, let me take up hybrid car. So the hybrid car has a mileage of 10 kilometer per liter. When it comes to your sports car, so it's around 4 to 6, I guess, 4 to 8, whatever. But yeah, it's less. So in a day-to-day language, we tell hybrid cars are more efficient than sports car. Again, we loosely use the word efficiency over there, but this is the funda. So for this amount of input, this entire thing is your possible output. So that's the funda of efficiency. We use efficiency directly and indirectly in our conversation almost every day. So with that understanding, we are looking at the efficiency of a heat engine. So the entire heading is thermal efficiency. So thermal efficiency, here too we have the same thing, net work output by heat absorbed. So obviously here efficiency will be equal to the effort will be in form of the heat coming in and how much work we are getting out of it. So this will be the entire thing. So we can further re-express this in terms of QC also. So let's do that. See, work will be equal to the net energy as per the first law of thermodynamics. Since we are not looking at any internal energy, no internal energy change, no. So let me start systematically. So we know that W or delta U is equal to Q minus or Q net in this case minus work. So with no change in internal energy, if there is no change in internal energy, so what we are looking at is delta U will be equal to 0, right? Because we are talking about heat engine. Okay, so this is for a heat engine. Because heat engine is not looking to make itself hot technically. So after a particular temperature, this will remain 0, and you have this two to be equal. So therefore you have delta U is equal to 0. And from here we can infer that work done is equal to the net energy per se. But the net heat supplied is equal to QH minus QC. Okay, yes. So then we have efficiency is equal to QH minus QC by QH, and that's it. So that is one of the expressions that we can have. Okay, then what else? I think, yeah, that's it. Okay, so what is that we are looking at? We are looking at the idea of efficiency. Efficiency is useful output by total input. In terms of percentage, it will be 100%. Definition of thermal efficiency: the fraction of heat absorbed from the heat reservoir that is converted to useful work. So your formula will be W by QH. And an expression over here, efficiency in terms of your QC and QH, basically in terms of heat coming in and going out. So technically and ideally, an heat engine will have delta U to be equal to 0. And you have, from first law of thermodynamics, Q net will be equal to W with this as a condition. So when you substitute, you'll get this answer. Thermal efficiency, the key takeaway is that we can clearly see that efficiency cannot be 100%. It has to be lesser. And the second law of thermodynamics for N is equal to 1 only if QC is equal to 0. So which is impossible. So we can also derive the idea of second law of thermodynamics, or we can see the aspect of second law of thermodynamics from this. If QC is 0, then you have efficiency to be 1, but QC cannot be 0. This we have explained. Its nature, things will flow from higher to lower. It's always the case. If a stationary object has to flow from one point to another point, either you have to put the effort. If it needs to happen naturally, then you need to have a lower potential that it's exposed to. So it can move from higher potential, lower potential, and you have a path connecting those two. So only then this is possible, right? With all of that understanding, with our basic understanding of nature, this is the conclusion that we are coming to, right? This is universal efficiency expression, valid for all heat engine. Doesn't matter if it's petrol, diesel, steam, Carnot, and so on and so forth. Okay, guys. So I'll leave to you guys what you want to write. This is an introduction part. And that is nothing but this slide. With this as the heading, you can write this derivation or that derivation. It's left to you.